Hello everybody. Today I'm going to go over a few more example problems. We're going to wrap up kinematic problems and then introduce and solve some free body diagram problems. So the first problem we have that you're standing ring toss, and all of these are like your classic carnival games and carnival rides. So the first one, with a ring toss, you stand 2.35 meters from a bottle. You plan to release the ring 0.25 meters higher than the bottle. The horizontal speed v naught x equals 7.8 meters per second. Determine the vertical speed you need to introduce to have the bottle catch the ring. And of course, g is 9.8 meters per second squared, and we're going to neglect air resistance. So the first thing, I'm going to draw this out. We plan on releasing it 0.25 meters higher. So here's 0.25 meters. We'll draw our little bottle over here. And this is 2.35 meters. And then our velocity vectors, I'm going to draw those in green. We have v naught y, we don't know, and we know that v naught x equals 7.8 meters per second. So the first thing we need to determine is how long this system takes. Since we have the x position, the final and the initial and the final, we can use the x of t equation to do that. So we can say that x of t1 equals 2.35 meters. So we know it's going to travel this 2.35 meters. And we know that that's going to equal our x naught. I'm going to set this as the origin, so this is 0, 0. So 0 is x naught plus 7.8 t plus 0 for the acceleration part. So we can just solve this for time. So you do, these are both zeros, so you end up with just 2.35 over 7.8 equals t, which equals 0.301 seconds. And then we can use that to solve our y of t. So we have y of 0.301 equals 0.25. This is the point that we're releasing it from, so our y naught, plus v naught y times 0.301 plus 1/2 acceleration, which we'll just call g, and then t squared, so 0.301 squared. So I'm just plugging in the time that we found earlier, and that's the time of, this arc. And then we're going to solve it for v naught y, because we know that over here we'll also say is 0. Really the bottle should be kind of down here because we're 0.25 meters above the bottle. So we know that it's going to be 0 equals 0.25 plus v naught y 0.301 plus 1/2 g 0.301 squared. And you can just solve this equation for Vy, and you get that V naught y equals 1/2 g t squared, with our t being 0.301, but I'm just going to solve it symbolically, minus 0.25, all divided by 0.31, so our time here. And if you plug this into the calculator, you get that v naught y is 0.696 meters per second. And that's the end of this problem. Okay, for this next problem, we have a duck gallery. You're standing 3.5 meters away from the targets. They move to the right at 0.8 meters per second. You fire horizontally. The muzzle speed is 15 meters per second. pellet is a point mass, and G is 9.8 meters per second. How early in seconds before a duck reaches the point directly opposite you must you fire so the pellet and a duck arrive at the same time? So we'll say that here is our duck, D. I cannot draw a duck, so this is a square duck. And we're firing at it from a distance here of 3.5 meters. I'll zoom out so you can still see the problem. 3.5 meters, and we have our velocity in this direction at 15 meters per second. And then the duck has a velocity in this direction at 0.8 meters per second. So we know that it's going to travel 3.5 meters. We know the speed at which the initial speed is going to travel, and we know that in the x direction at least, it's not going to have any acceleration. So we can solve x of t equals 0. We'll set here as 0, 0. So that's our x naught plus v naught x, which is our 15 meters per second times time, and then plus 1/2 0 times squared. So both of these terms are just 0, and we know that at some time we need it to travel 3.5 meters, because that's how far away the target is. So we have 3.5 equals v naught x, which is 15, times time. And so if you solve this, 3.5 divided by 15, you get that our time is about 0.23 seconds. So that actually solves the first question, how early must you fire the pellet? Because we've determined that it's going to take 0.23 seconds for it to travel that 3.5 meters. So if you fire it 0.23 seconds before before the duck reaches the point directly opposite you, that's the time you need to fire it before. So the second question is, at what height above the duck's center should you hold the muzzle so the pellet fired horizontally hits the duck's center? So in this case, we have y of t equals y naught plus v naught y times time. We know v naught y is 0. There's no initial velocity in the y direction. And then minus 1/2 gt squared. Minus because g should be negative. And we're solving for y naught because we're asking at what height above the duck's center should we fire. So solving symbolically first, we have y of t equals y naught minus 1/2 gt squared, or very simply, y of t plus 1/2 gt squared equals y naught. And then we know that our y of t, so the point that it hits the duck, we'll call that 0 to make this term 0. So that means y naught is just 1/2 gt squared. We already found the time that this is going to take earlier, so if you plug all this in, 1/2 g times 0.23 squared, you get your answer, which is about 0.267 meters. And this is equal to our y naught, and the height above the duck's center, you should hold the muzzle. Okay, so the last question is the last kinematics problem, and now we're going to move on to some force diagrams, some free body diagrams. I'll let you read all of this. The givens, so the important things we already have. But basically we have a ride moving in a vertical circle. And here, I'll show you a picture of the ride up here. So one of these spinny rides. And we know it's moving in a vertical circle at a constant speed of 100 kilometers an hour. And we want to draw a free body diagram, label all forces, and indicate the direction of net force. So one key thing we want you to do is that gravity is vertical and does not enter the tangential force balance at the bottom snapshot. So your free body diagram, here's the bottom of the ride. There is, we'll say it's traveling to the right. There is a drag force trying to prevent that. There is a forward force to counteract that. We'll call it FA. And then the net force is going to be in this direction. And the reason for this is we know that we know this is uniform circular motion because it travels at a constant speed. So the net force is a centripetal force that keeps it in that uniform circular motion. So that's our free body diagram. Next question is how much force the ride needs to introduce to account for the drag force. So if we treat the drag force and the other force to counteract it as purely horizontal, we can just say that F net x equals 0. We know that it equals 0 from the equation F equals ma. We know that it's a constant velocity, so it's not accelerating. So F net x equals 0 equals the force of the drag minus the force of A. And so we know that FA is negative because they're in opposite directions. You could also say that FD is negative. It doesn't really matter which one you choose to be negative. It's up to how you decide your axes. But you can pretty easily see that FD equals FA. And since we already know FD is 1/2 rho CD AV squared, we can just plug all of that in to determine how much force the ride needs. If you plug all of the constants into that equation, you get that this is equal to 324 newtons. Last question says determine the inward acceleration allowing the rider to travel in a uniform circular motion. So I already mentioned that with this F net in the y direction being our centripetal force. For acceleration that is purely centripetal, so it doesn't have any components in the x direction, the only direction that it is accelerating is centripetal in order to maintain uniform circular motion, so circular motion that isn't speeding up or slowing down. The equation we use is that centripetal acceleration is equal to the tangential velocity squared divided by the radius of the circle. We know that our tangential velocity is 100 kilometers an hour. We know that r is 31.5. So if you do that calculation, let me plug it into the calculator real quick. We have 100 times 100, and then divided by 31.5 is a number that's a little bigger than I expected. Let me double check this real quick. Okay, I see the problem that I had, and I'm actually really happy that this problem happened, that I overlooked this because it's a very good thing to point out. The velocity is given in terms of kilometers per hour, whereas the radius is given in terms of meters. So we have to convert velocity from kilometers per hour to meters per second. I went ahead and did this already because at this point in the course we've done this plenty of times, but 100 kilometers per hour equals 27.7 meters per second. So if we square that, let me plug it into the calculator real quick, 27.7 squared, and then divide that number by our radius, 31.5. We get our answer. Centripetal acceleration is roughly equal to 24.35 meters per second squared. And that is the end of this problem. Okay, for this next problem, we have another force problem with a ride that looks like this. Maybe you've been on one of these. I think I rode one once called a Gravitron, which was a lot of fun. But we have a ride spinning in a circle. Plane is tilted 80 degrees above the horizontal. Constant speed snapshot, so we know it's a uniform circular motion at the highest point, given that R is 4.5 meters and A being 80. Oh, that's an alpha, sorry. So that's our 80 degrees. Analyze a single instant when the rider is at the highest point of the ride. Your friend who's riding with you says, "I'm being pushed outward against the wall." How would you respond to correct your friend? So we know that there isn't really an outward force. There's nothing on the other side of the wall that's pulling him against the wall. What's really happening is that his own inertia is keeping him pinned to the wall. If you can imagine the path of motion, it's going like this. But at any point, the velocity is tangential to this motion, like this. And so what he's really feeling is that his velocity wants to continue in this direction, but the wall is preventing him from doing so. So he's feeling his velocity, his inertia, but the wall is preventing him from doing that. If you were to take this and he's spinning in a circle and then all of a sudden remove the wall, he would just fly in a straight line in this direction. And this may make a lot more sense after question 2 when we draw our free body diagram. So we have the alpha here is 80 degrees. I'm actually just going to draw a picture of this first. We'll say that here is kind of the box, the system with you and your friend and the wall you're being pushed against. There's a frictional force, first thing, in this direction. And reason for that is if there was not a frictional force, you would kind of just keep sliding off. There's a normal force in this direction because you're making contact with the box. And there is a force of gravity in this direction. Sorry, this is N and this is Fg. And this is just equal to mass times gravity. And then we know that this alpha equals 80 degrees. So we can draw our triangle to determine the x and y components. I'm going to say that this direction is the y direction and that this direction is the x direction to more easily do my calculations. There we go, that's better. Because we know that this Fg equals mg and this angle alpha is here, we know that this angle is also alpha. This is obviously not drawn to scale, but that angle would be our alpha, and then this would be our right angle. So from trigonometry, we know that this is mg cosine of alpha, and then this is mg sine of alpha. And again, that's just because this part is the mg, the force of gravity. So in the y direction, moving on to the next question, because we've done our free body diagram now, and the indicate the direction of the net inward force. That is the normal force there. So determine the minimum inward acceleration required so that riders do not lose contact. So the first thing we're going to do here is we're going to say F net y. The net forces in the y direction have to cancel because you're not sliding up and down the wall. So F net y equals 0, and then this is equal to our frictional force minus mg cosine of alpha. Because here's a force in the y direction and here's a force in the y direction. And then F net x, this is going to be our centripetal force, because our x-axis we've decided is in the direction of the centripetal acceleration, because centripetal acceleration is always going to point directly towards the center of the circle. So this is going to equal we'll say it's negative force of centripetal acceleration, so that this direction is negative. And then this equals negative mg sine of alpha, because this force vector is in the x direction. It's negative, and then minus the normal force. An interesting thing you might have already noticed about this system, though, is that even though there is technically some sort of normal force because you're making contact with the wall, you can set it equal to 0. The reason being because there's no force in this direction to cause that normal force. So yes, you're touching the wall, but there's nothing, no force in that opposite direction to cause that. So we now have negative force of centripetal force, which is just mass times centripetal acceleration, equals negative mg sine of alpha. We weren't given mass, but you'll see it doesn't matter. We can cancel both of these negative m's, and we can just say that centripetal acceleration is equal to g sine of alpha. And then these are all things that we know. G is 9.8, alpha is 80 degrees. If you plug those in, you get that AC is equal to 9.65 meters per second squared. Okay, the next question is the speed of the ride to determine this inward acceleration. You may recall from the earlier problem that centripetal acceleration is given by v squared over r. And we were given r in meters. And then since this is already in meters as well, all we have to do is solve for v squared. So multiply both sides by r, take the square root, and we get that v is equal to the square root of the centripetal acceleration times r. And then if you plug both of these in, you get that the velocity is equal roughly to 6.59 meters per second. And that is the end of this problem. For the next problem, we have one of these spinny chair rides, which I have ridden one time, and I very much did not like it. I normally like roller coasters, but I really didn't like this one. Too high, too scary. So we have a 55 kilogram rider sitting in a swing, that's the mass, suspended by chains 6 meters long. When it reaches a steady speed, so once again we're working with uniform circular motion, the chains are at a 40-degree angle with the vertical. Uniform circular motion, no wind, and massless chain. Now we're going to do another single steady speed snapshot. First thing is to draw our free body diagram for the rider, including the direction of net force. Let me get us another page here. I'll do the free body diagram up here though. So we have the chain coming down here. Here is our rider. That's kind of all there is to the diagram. So once we do the free body, let's see, I'll do our forces in red. There's going to be a tension force along the chain, and of course a force of gravity straight down equal to mg. The direction of motion, we'll do that in blue, or the net force in order to keep uniform circular motion is in this direction. And then this angle here is the angle from the vertical, because here is vertical. We'll call it, we'll just plug in the actual angle is 40 degrees. So that's question 1. The next question is, what is the radius of the rider's circular motion? So we already know that the chains are 6 meters long, 6 meters. And we know this 40-degree angle, so we can use trigonometry to calculate this part, which is the radius of the rider's circular motion. And then that would be 6 sine of 40, because it's opposite the angle. If you plug that into the calculator, it's 3.86 meters. Next question is the tension in the chain. And that one's going to be much more interesting. So you can break the chain up into two components, the x and the y direction. Since we know the force in the y direction from gravity, I'm going to use that one first, because right now we don't know anything about the x direction. So F net y, we know has to equal 0, because it's not moving up and down. It's moving at a constant 40-degree angle. And this is going to equal t cosine of 40. So if you draw your triangle here, this angle is 40 degrees. T cosine of 40 minus mg. You can just solve this for t, and you get that T, which is our tension, is equal to mg over cosine of 40. The mass is, 55 kilograms. The theta is 40 degrees. G is 9.8. You plug all of that into the calculator. Let me plug it in real quick. So we get 55 times 9.8 divided by cosine of 40 degrees is 703 newtons. So I'm going to double check that real quick, but I think that that's right. 55 times 9.8 is 539. And then divide that by cosine of 40 degrees. Should be, 703 newtons. Okay, so the next question is, what is the speed of the rider? So in that case, we need to first determine the centripetal acceleration of the rider. Going to come down here. For that, we're going to need F net in the x direction. We know that this is going to equal mass times centripetal acceleration, because we know that the net force in the x direction, we're dealing with uniform circular motion. And we know that in the x direction, the only component is t sine of 40. We already found t is 703 newtons. And so you can plug this in for the centripetal acceleration first. So t sine of 40, if we divide both sides by m, we'll get our centripetal acceleration. AC is equal to about 8.22 meters per second squared. I'm going to double check my calculations real quick. But tension times sine of 40, and then divide that by 55. 8.22 meters per second squared. This is our centripetal acceleration. And we know from earlier that centripetal acceleration also equals tangential velocity squared divided by radius. Use the same equation as earlier, and we get that v is equal to the square root of centripetal acceleration times radius. We already found the radius of our circle earlier. That was our 3.86 meters. So if you plug in 8.22 for centripetal acceleration and 3.86 meters for our radius, you get about 5.63 meters per second. Not meters per second squared, because this is velocity. So the last part of this question is a conceptual analysis, where we suppose the speed of the ride increases while the chain length and rider mass stay the same. First part is, will the angle between the chain and the vertical increase, decrease, or stay the same? And the answer is that it will increase from the vertical. Reason for this is, since the speed increases, so this part, but the chain remains the same, the acceleration will also increase. Technically, our vertical radius will, or the radius of our circle will also change, but since speed is squared, it's a bigger, more important term, and so the acceleration overall increases. And then since centripetal acceleration is based on t sine of 40, which is that is a, what is it? It's in the x direction. The overall x direction increases. So the angle has to increase as well. As the speed increases, how will the radius of the circular path change? The radius is also going to increase, because if you imagine the speed increases, let's say we have it here, and this is our 40 degrees. As the speed increases, the angle increases, and so this radius from the center is much larger. And then finally, how will the tension in the chain change with increasing speed? The last question here asks, how will the tension in the chain change with increasing speed? And as you may have already guessed, similar to A and B, the tension will also increase. The reason being, because in this case, where the angle has increased and the radius has increased, the tension is the thing that both counteracts the force of gravity. So there's a force pulling downwards, and it also has to provide the centripetal acceleration in this direction. Since the acceleration is increasing, the tension has to increase to match that. And that is the end of this problem. For this last problem now, we have a roller coaster. Here's a generic roller coaster picture. We have a 55 kilogram rider sitting in a compact coaster car. At one crest, the vertical acceleration is downward, so negative 0.5 g. At the next valley, the vertical acceleration is upward with magnitude 1 g, so that's positive. Assume two steady speed snapshots for the crest and the valley, and treat the track locally as circular. So each crest and each valley should be treated as circular motion. And then the first question is to draw a free body diagram for the crest and valley and include the direction of the net force in each case. So over here, let's do the crest. And then over here, we could do the valley. So for the crest, here is our coaster car. We know that there is some force of gravity, mg, and some normal force acting in this direction. And we know earlier that the acceleration is negative 0.5 g downwards. So it's accelerating downwards. And we'll use that later in our force equals mass times acceleration problem, or equation. For the valley, here's our coaster car, here's our normal force, it's still touching the track, and then here is mg, and our acceleration was equal to 1g in the positive direction. So that is the free body diagram for each. The next question is, what is the rider's apparent weight at the crest? And then what is the rider's apparent weight at the valley? So dealing with the crest first, we can solve F net in the y direction is going to equal n minus mg. We'll say that down is negative in this case. And then that will equal our mass times this acceleration. So negative 0.5 mg. So if you add mg to both sides, you'll notice this is 1 mg and this is negative 0.5 mg. So adding it, you get that n is equal to 0.5 mg, because negative 1/2 plus 1 is positive 1/2. We know mass, we know gravity. If you plug both of those in, a reminder that mass is 55 kilograms, gravity is our constant. You get that n is equal to 269.5 newtons. For the valley, you use the exact same method. For F net in the y direction, we still have n minus mg. Those are the only two forces acting. And then that is going to equal positive mass times gravity, because this is 1g in the positive direction. Add mg to both sides, and you get n equals 2mg. Plug in your 55 kilogram mass and your 9.8 gravity, and you get that n is equal to 1078 newtons. And that is the end of this problem and the end of this video. As always, if you have any questions or comments, please leave them down below, and I will answer them as quick as I can.